Okay, let's get started talking about linear maps and bases. So the linear maps can be, we've usually specified them by a general formula so far. Here's the general formula. So this is an example, like we have a map and it goes from say x, y to 3x plus 4y, 5x plus 6y. This is a map from R2C to R2C, okay? Well, this is the general formula which we give the, is in terms of the components of the domain vectors. Okay, now we can also specify it in a separate way, which is will be useful in making the transition to linear maps and matrices. So the way we do this is we can specify, say, the map G by choosing a basis here, and we specify it by a basis action. So let's say that we just use the standard basis for V2. This is going to be a different map, and then we just say this goes to say 1, 2. And then we have to also give the other basis element. Say this goes to 1, 4. Okay, so we have a basis section, and this specifies a map. It's called, I mean, we can make many maps for which this is true, but there's going to be one unique map that's a linear extension of this. So if we want to sort of recover the general formula from this one for G, what we can do is we can say, well, we want to know what G of a general form is, right? Well, that's going to be equal to, because we're given a basis here, 1, 0, 0, 1 are two basis vectors for R2C, we can represent, this vector essentially means we have x times 1, 0 plus y times 0, 1. So, and this is what's called the standard basis. So the advantage of expanding the general vector in terms of the basis is we can, since if we want G to be linear, then we can apply linearity to this, and that's going to be G of 1, 0 plus y of the image of 0, 1. And that's exactly what we know here. So we can plug those in to get x, the image of 1, 0 is 1, 2 plus y times the image of 0, 1, which is 1, 4. And then we can combine these together to get x plus y for the top component and 2x plus 4y for the bottom component. So that G takes xy to x plus y, 2x plus 4y. So this shows how to start from a basis action and go to the general formula and recover the linear map that's consistent with that. So, okay, well, we could go the other way, of course. If I'm given the general formula here, I can just put in 1, 0 and 0, 1 for the basis vectors, and I'll get out values for these ones, for the images, which will be exactly those vectors. So I can go back and forth, and either one is adequate. And there's a problem on regex that someone asked me about, that where they weren't sure what was going on, and this is what was going on because we had skipped over this in the earlier part of covering the material in this chapter. And this is on page 335. There's a the general result is a linear map is determined by its action on a basis. If V is a vector space with basis beta 1 through beta n, and W is any vector space, given any n vectors in W, they don't have to be distinct, then there exists a linear map which sends beta 1 to beta 1 to W1, beta 2 to W2, and that linear map is unique. And that's what we did here. I just chose two random vectors here. I can choose any of them, and I'm going to get a linear map by this process. Okay, is that clear what's going on for that?